Gives us a link to the next presentation because we need safety for all of this in the future. So we'll call Mr. Sébastien Agostini from the company ClearC, specialized in safety systems and vital solutions.
Hello. So good morning to everyone. Thank you to Sébastien.
This is the afternoon, in fact.
Good afternoon, so. Sorry about that. So thank you. I'm pleased to have the opportunity to introduce ClearC and the ClearC safety platform, the safe calculator we develop, and myself too. So my name is Sébastien Agostini. I'm business unit manager for the electronic and embedded system department in ClearC. So for beginning, maybe a few words about ClearC. We are a design office, a French company, specialized in safety critical system and in design safety solution. We are the author of the formal method Atelier B. Just a few words about the formal method. It's a way to mathematically prove software compliance against the specification. And we work worldwide. 20% of our turnover is abroad, but always with safety matter. So today I introduce, as I said, the ClearC safety platform, which is a package, and it's a SIL4 system, including the calculator, so in terms of hardware, of course, the calculator, and a starter kit in order to implement it for prototyping purpose. We also included software, the firmware and the safety firmware of the calculator in order to ensure that all the execution is made in a safe way. And we also propose all the tool chain to integrate the environment and the necessary tool to load, compile, and so on the calculator, the final application. And of course the safety case, because it's a SIL4 system already certified, ready to market, with all the guidelines to implement it in safety. So why we propose this kind of system is because we already implement that kind of architecture on past projects. So I have some example here with the control command screen doors for Sao Paulo and Stockholm, which implement that architecture, and more recently for remote I/O, an interface with CBTC that have the particularity to be compliant with the Senelec standard, of course, so EN 50, 128, 126, 129, but also with the AREMA standard, which is the equivalent in North America. So in terms of hardware, it's a SIL4 component ready to integrate on the design. As you can see, it's a compact size required to be integrated on the motherboard. It's a versatile product because all the peripheral of the microcontroller is available on the connector, and so it's up to the final user to develop the peripheral and the interface to be fully compliant with the project and with the requirements of it. And of course, it's low consumption. It's based on true microcontroller from microchips, so it's less than 2 watts, and it's based on a 2 out of 2 architecture in terms of hardware. We associate it to a starter kit, a jumpstart system to make the prototyping easier and to implement some proof of concept based on this calculator. So we propose all the toolchain to be complied with and to help to develop this product. And so we integrate also on this starter kit the interface, the standard interface like I/O logic, serial communication, Ethernet, and so on, USB, all that can be used to develop prototype. In terms of software, we also developed a basic firmware to be integrated on the low level of the hardware with some primitive to be called for safety purpose and for final application purpose. Already installed on the calculator. And in terms of development, you have at the top level the specification in native language, which has to be implemented in B0, which is a subset of the B language, formal language. So after the specification, you have the implementation of the source code, one unique source code, and 2 channels of compilation for diversification and for safety purpose, to have at the end of the compilation a concatenation of what we call the 2 replicate, which is 2 different binary from the same source code but with the same behavior. And so when you download these 2 replicate on the microcontroller, based on the fact that they have the same input and they have the same behavior, we are able to check at each cycle that there is the same output from the 2 replicate, and so ensure the safety of the execution. So it's a composite safety execution with 2 out of 2 per microcontroller execution of the software. Okay, next please. So we have also the toolchain, as I said, because for safety purpose, of course, all the tools for compilation, downloading, and so on have to comply with all the Senelec standard and all the safety purpose. And so we aggregate all these items in a tool, completely hidden by the end user to make it easier for them they have only to compile the system and to obtain all the binary file ready to download on it. And so all the primitives are completely hidden to the end user, and they are only to start a command. Today the input of the implementation is the B language, so B0 here, which is a subset of the B language, really comparable to C or ADA, but there are various strategies to implement it in the B language. You can write manually, you can generate it in order to have the benefit of all the formal language in terms of validation, in terms of mathematical proof of the software. But you also can use past source code in another language, for example C, ADA, or something other, and have the capability to translate it in B language to have the right input of the toolchain. Okay. So how can it work? If you have a project, if you have an implementation to be done, the first step is to design the interface in terms of hardware. I mean that kind of calculator have to be docked or to be fit on a motherboard, and so all the specific interface have to be designed to be comply with the project and its interface. So in terms of hardware, we need a motherboard. In terms of software, of course, the basic safety firmware is already available on the calculator, but you have to implement the final logic, the final application of the software on the calculator in B0. And at the end, you have to write and to demonstrate the safety by a safety case. So there is some item to comply with. First of all, you have the certificate, the SIL4 certificate of the calculator. You have to comply with the safety application condition of this calculator to be SIL4. And to help you on do that, we made some guideline and checklist to make certification easier. Okay. So I will introduce an alternate solution to localization, which use that kind of safety platform. It's based on two equipment on board. I mean a sensor and a control unit. And it also includes a magnetic loop on the way side. So this magnetic loop is in fact a very long antenna, 300-meter antenna, all around the track, between the track. And this antenna includes two different magnetic loops. That's schematic here on the picture in the middle. So you can see here that there is a blue one, an irregular magnetic loop here that allows to communicate with the train and to send him some identification. It's a kind of barcode for the train to identify on which antenna and on which sector of this antenna the train is. It's a kind of large localization. And based on this first point, the train can be localized precisely by the second magnetic loop, which is red here in the picture. And that allows to the train to count every regular edge of the magnetic loop to have a better accuracy, because between each edge there is 20 centimeters, and the train can see each edge and to see where it is in the magnetic loop. So it's okay. So the safety is only based on these three aspects with the automatic test and the two magnetic loop to communicate with. Thank you. In terms of hardware, you have here an example of the motherboard, where we can see that there is the Clear-C safety platform on the left in blue, and there is two independent channels connected to this calculator for sensor the magnetic field. And this redundancy is for safety for sure, but it's also because we need to test regularly that kind of channel. And so there is a combination of two channels twice, because when you test a two channel, we can count on the previous one and make an inversion to test the other channel. So it's a redundant for safety, but there is a double redundance to allow to test each channel. And at the end of the day, with this application, based on the SIL4 certificate of the calculator, based on the hardware we design, and also based on the formal mathematical proof we have on the software and on the system at system level, we can have the demonstration that the train can give its localization precisely, with tolerance, of course, based on the worst case of failure and based on the 20 centimeters between each edge, but a SIL4 localization for the train and the speed of the train. As a conclusion for the safety and regarding the Clear-C safety platform, we propose today a safe calculator ready to market, which include all the safety requirements in terms of software, in terms of hardware, to develop turnkey application ready and really specified to the project. Of course, there is a work to adapt the interface on the motherboard, and of course there is the final application software to implement on it. But it is based on mathematical proof, and based on this fact, we can make the development, the certification shortly and easier. And based on the strength of formal method, we can also save time for validation, because the mathematical proof make the validation, the unitary test, easier and simpler to be more efficient in the SIL4 system development.
Well, thank you again, Sébastien, for this presentation about safety.